Recording is rolling. It is Thursday, February 6th. So we're doing stuff with fluids. Here I didn't make my list. Is you guys know AP night's 1 week from now. If you want to present to the 8th, 9th, 10th graders coming up, tell them about AP, then go see Mr. James about that. Right. So stuff about fluids. I'm going to review some of these concepts with you guys really fast. And then I'll do a couple examples for the guys on, well, these two here, conservation, flow, and Bernoulli. Right, so, and the other ones I'll hit real fast. Right, a few days ago, I gave you guys these chapter 9 puzzles. This is going to be our main focus today. Right, so if you guys have those out, we're working towards that eventually. Here's the way I'm going to assign these. Is numbers here? If you flip this over, there's some warm-up puzzles on the back. Now some of these are solids. I don't know. I just put their whatever, right? So you guys are focused on these fluids. You guys see numbers 6 through 11 are fluids, and these are warm-up questions out of your textbook. So I checked these, and all the main ideas show up here. I gave you guys a checklist the other day. You guys remember I said ABCP? You guys remember ABCP, right? That could stand for Archimedes, Bernoulli, conservation of flow, and Pascal, right? So there are principles going on there. Number 6 through 11, check all the boxes. So that's going to cover all the bases. So I want you guys to do each of those, number 6 through 11. That's what 6 different questions right there. Okay. I want everybody to do number 38. You guys number 38 in the main puzzles, right? Which we had probably this one before. Right? If you paint something from a scale and then dunk it in water and you see differences in forces, differences, right? You can calculate what's the density of the object. Okay. Okay. And 3 additional puzzles, which I'll get to that later. Okay. You guys have AP Classroom that's been open for a while now. So fluids questions. Can you guys have this done by the time come class Monday morning? Right, so we can go over the solutions then. Right. And then of course I returned your rotational dynamics quizzes, and your stickers are they're scented. So you guys can smell your stickers. Yay. All right, so let's do a quick review. Go ahead. Yeah. Okay. Well, I got a couple left. All right. All right. So, quick review. You guys remember Archimedes principle? Guys, this was the theme of yesterday's lab. You guys remember building some boats? Right. So you took a flat sheet, build into a little box. Right. So the principle here is that anything that's either submerged or partially submerged in water or floating in water, there's an upward force acting on it, which is buoyant force. Guys, why does the buoyant force push upward? Why does it push upward? Yeah, because because the deeper you go, the more the pressure. And if objects are 3-dimensional, right? So overall there's an upward force, right? And now the magnitude of that force turns out is equal to the weight of the displaced fluid, like the weight of displaced water. And you can break that down into it goes like this. So here's m times g for the water. And I know mass is density times volume. Actually, you guys know density, right? Density is mass per unit volume. Can you guys rearrange that and get mass is equal to density times volume? Can you guys do that? Right? That's all this is right here. Is that? Right. So you've got to follow in. Guys, rho VG, or sometimes you see it rho GV, sometimes different orders. That's okay. Right? Guys, this rho represents what? Density of what? Density of the object or density of the water? Fluid. Water, the fluid. Yeah. All right. Right. You guys have that? Right. Quick follow-up from yesterday's lab. Some of you guys turned it in yesterday. Some of you guys finished the graphs and turned it in today. I see some in the grade tray. Guys, what was the solution to this? Like, if you start bending up the sides, so you want to build like the biggest size boat and carry the maximum cargo. This was 12 by 12 centimeters, right? How much should you fold up each side? What did you guys get? 2 centimeters. You guys got? So fold up each side 2 centimeters. So that would give you dimensions of what? 8 by 8 by 2, I think, right? And that would be the maximum size boat. Right. All right. So you guys get on Archimedes. Okay. Of course, you guys know the density is mass per unit volume. Do you guys know what? All right. But here, I'll tell you guys a story. You guys know why there's a crown in here? Yeah. What's the story with that? Yeah. How's it go?
Well, it's the king told him to check if the crown's pure gold. He was trying to find ways to test that out, and he found out that the density of gold and silver is different. So the side that has silver is gonna glow.
Well, yeah. Okay. So yeah, it has to do with density, right? So it was this guy, Archimedes, right? Oh, so there was a local king because they had those little city states with these kings. didn't know what was this crown pure gold or was it mixed down with other metals, right? And you could know if you knew the density. Density is mass per volume, but how do you get the volume of some weird thing? You guys, oh, well, if you throw it in water, then you can watch the water level change, right? So supposedly he had this epiphany when he was lowering himself into a bathtub and he watched the water level go up. He said, oh, that's how I can get the volume, and I can get the mass by putting it on a scale, get the density, right? According to legend, shouts Eureka and runs through the streets naked. So, yeah, all right, with India. Go to jail nowadays, but back in the day, yeah, that's how you did science. Okay. So, here's a fun question. Here. All right. Okay, so you guys had a free body diagram on your boat yesterday. It looked like this, right? The weight down, buoyant force up, balanced out, right? And pressure has a really similar looking formula. Guys, compare these two formulas. Buoyant force, rho vg, pressure is rho gh, right? So instead of depth, you could replace that with volume to go from pressure to a force. I guess that kind of makes sense to you, right? Okay. All right. Here's a fun question: suppose there's an ice cube floating in your drink, or suppose there's an iceberg floating in the ocean. Do you think the same proportion of ice is submerged? Yeah, as long as it's the same densities and materials. Okay? And you can solve that, like what percentage of an ice cube or an iceberg is submerged in water. Okay? Well, here, you guys can see the solution here, but turns out it ends up being, at the end of the day, the ratio of the densities of these materials. Right? Ice is less dense than water, so it floats. Right, got that. I showed you guys this yesterday, so quick recap. Every time you see it, right, helps your brain learn a little bit better. Right? Well, I know that the pressure is the same down here. That's Pascal's principle. Pressure is the same here as here. Pressure is the same here as here. Right? Now, when you go up into these fluids, well, you actually have different individual pressures at different elevations because you got different fluids going on. Right? But for the same fluid, it's the same pressure at the same level. Right? Okay? It's called Pascal's principle. Okay? Right? So how can you set up an equation to either solve for, like, what if you didn't know the density of some material, or you didn't know how much you have to fill it to, like, how do you make these heights work? Right? So it goes like this. The pressure build up to here, I got this rho gh naught plus this rho gh1 plus this rho gh2. Now, it's different rhos because it's different density materials. Okay? Plus the atmosphere. Don't forget the atmosphere. I have this YouTube, I have both ends open to the atmosphere. Right? There are variations on this. That's not always true. You can cap one end. You can have one end pressurized. Right? But I just got both ends open. Right, okay. On the other side, I get this rho gh naught plus this rho gh3 plus this rho gh4 plus also the atmosphere. Okay. Now, since the atmosphere is acting on both sides equally, I can cancel that out. They both have this rho gh naught, which is same material, same height, so that cancels out. But these four terms could be different. Okay. Right. And you guys can set up an equation and solve that. Okay. All right. You guys remember Pascal's principle? This I just referenced, right? So it's the same pressure on both sides. Pressure is transmitted and diminished. I think I'm gonna go back and delete this bullet point here. You guys see equal pressures and equal depths. That's only true if it's the same fluid, right? Which would not be the case for, like, I couldn't say it's true like here, right? Okay. And it's also true if it's stagnant, so it's not flowing. Which the examples I'm about to do with you guys have fluids in motion, right? You guys ready to put fluids in motion? Okay, so far fluids have just been static. That's static. That's static. Okay, that's static. It's not like none of these are moving, right? These are all static scenarios. Right, but let's put this in motion and see what happens then. Right, so I got two posters on this. This is going to be here. Go to my checklist here. Okay. Oh, you guys see conservation of flow and Bernoulli principle? Conservation of flow and Bernoulli principle. All right, you guys ready to maybe take some notes here? Okay. So conservation of flow. So you got water flowing through a pipe system. Could feed into big pipe into a small pipe is what I got here. So let's set up like that. Big pipe feeds into a small pipe. Big pipe, small pipe, right? So like this. Okay. And let's say I section off some cross-sectional area. Okay, and look at, let's make a little cylinder, a little flat cylinder, sideways cylinder. So I got some volume here. So I got some cross-sectional area A1, and I got this distance, call it X1. It's okay? Okay. Could the volume of this cylinder right here just be this area times that X, right? Okay. Right. And then I'll section off, let's say a same volume over here, but it's a little tiny area, A2. And I'll call this distance X2. Okay? Okay. You guys see it's equal volume? Okay. Now, this term right here, conservation of flow. In terms of American units, could that be the same gallons per minute everywhere in this pipe system? Right. Suppose this is 1 gallon and this is 1 gallon. It takes it a minute to flow. It could be both 1 gallon per minute, right? Right. And then in this class, of course, we're doing cubic meters per second. So if this is a cubic meter and a cubic meter, it takes them each a second to move. That is okay. Okay. So I'll say volume 1 over time equals, well, volume per time is volume per time. Actually, maybe it's the same volume in the same time, and they're both moving. That's conservation of flow right there, right? But what is volume in terms of this area and this x? What could that be? How can I substitute out volume? This is just area times x, right? Right. So cross-sectional area 1 times x1 and some amount of time equals cross-sectional area 2 times x2 in the same amount of time. That's okay, right? You guys can believe that? Okay, I can believe that. Okay. Now, what is this right here and that right there? What's distance over time television? Speed. Aha. You guys see cross-sectional area times speed? That product is the same everywhere in this pipe system. Aha. You guys see that? Okay. So cross-sectional area times speed. Okay. So, for example, we'll throw some numbers on here. Let's say the first cross-sectional area is like, about 4 units. I don't know, maybe it's like square meters, 4 square meters. Okay. And I got a speed here, got the speed going through here. Call it V1 of like 6 meters per second. Okay. Okay. And then this cross-sectional area 2. Okay. Let's say that's a quarter as much. So now we're down to 1 square meter. Okay. Guys, if you make it narrower, 1 square meter, what do you think the new speed is? What is that? What's 4 times 6? 24. 1 times what is also 24? 24, right? And that'd be meters per second, right? If I tag my units to those numbers, right? Is that okay? Right? Okay, so if you have a smaller cross-sectional area, what happens to the speed? It gets faster. Yeah.
So does it, if you multiply, or so you have the area of the first one?
Yep.
The area of the second one is 1/4 of the first one, so you multiply the speed by 4. Portion.
Yeah.
Okay.
There you go. Yeah. So 1/4 of the area is 4 times the speed, right? That'd be conservation of flow. Right. Right. Of course, there's different takes on this too. A lot of times, guys, it's really common to identify pipes according to their diameter. Right? Who could tell me? Well, let's say we're playing around with these numbers right here. Now, my picture is not to scale, so oops, sorry about that. But what is if these numbers are true, what is the diameter of this pipe compared to the diameter of this pipe? Because I see the areas are a ratio of 4 to 1. That means the diameters are a ratio of what to what? Guys, what's this? Here. What's the area of a circle? Pi r squared. So area is pi r squared. Okay. Now in terms of diameter, that'd be pi over 4 times d squared. That doesn't really matter. Isn't radius half the diameter?
Yeah.
If you square that, pull it out, it looks like pi over 4. Okay. But that doesn't even matter in terms of proportions. Actually, this doesn't even have to be circular. You could have a square pipe or a pentagon pipe. Okay. Okay. Right. This would still apply. Right. So if I have 4 times the area, how do you get to the diameter? You have to take the square root. What's the square root of 4? 2. Right. So if I drew a picture to scale, how should I draw it to scale? Whatever diameter this is, this should be how many times the diameter? Half. It should be half if my picture was to scale and match my numbers down here. You guys see it? Right. So you have half the diameter corresponds to 1/4 of the area. Yeah.
Do you not consider the fact that it's a cylinder?
Yeah, it doesn't even matter the shape. This could be a pentagon shape, right? And this could be a pentagon shaped pipe, right? And the relationship between like how wide across and the cross-sectional area is still a squared relationship. Yeah. Okay. You have a square pipe. Okay. It doesn't really matter the shape of the pipe. Okay. Right. So it's like a scaling question. Right. Right. That's good. There's a conservation of flow. Right. Now, let's throw a little fish in here because this is going to lead to the next one. Oh, whoops. Actually, I forgot. Before we get to the fish, one more little detail. I don't think this is probably going to matter so much, but you guys see where it says for incompressible fluid, A times V equals A times V, right? What if you had something that was compressible, like air or something? Like air could be fairly compressible, right? It's like a gas, right? You also have to consider the density. You have to throw that in the mix because if it gets more dense, then it would slow down, kind of thing. Right. Okay. So you could also navigate that too, right? Right. Yes, sir. All right. Let's go back to this fish. Look at this fish. He's swimming around. Right. Do you think there's probably he feels like there's some internal pressure, kind of like if you dive down a few meters into the pool, feels okay, he feels some pressure. Okay. Now when he goes into this little skinny pipe, does the water slow down or speed up? Speeds up. Okay. What do you think the fish feels like happens to the pressure? Is it the same pressure or is it a different pressure?
Bigger.
It will be a different pressure. Okay, now this might be a little counterintuitive, but actually, let's solve this right now. I'll show you guys with a scientific demo right now. Right? The fact that you guys told me the fluid speeds up, that's what you guys just said, right? Let's try it with this paper right here. I'm going to blow a stream of air over the top. Wouldn't that be speeding up the fluid over the top? Wouldn't that be doing that?
Lower pressure.
Right? Yeah. Catch on this. Is that going? Oh yeah. Oh, yeah, here, go ahead. Go. All right. All right. So when I blow a stream of air over the top, that would be speeding up the fluid. Right. Question is that going to push the paper down, which would represent an increase in pressure, or is it going to vacuum the paper up, which would represent a decrease in pressure? Show of hands. How many of you think that when I blow a stream of air across the top, it's going to vacuum the paper up? Who thinks that? Who thinks that? Huh? Who thinks it's going to push it down? Who thinks that? Huh? Let's see. Let's find out. Do some science. It is vacuuming it up. You guys see it's vacuuming it up? Okay. So just some science right there. Show that a faster moving fluid does a decrease in pressure. So when this fish goes from this big pipe into the small pipe, does it feel like he went near the surface of the pool or went way down deep into the pool?
Surface.
It feels like he went near the surface. It feels like there's a pressure drop, like the pressure just decreased, right? Right. And I'm trying to get to something that what principle am I trying to work towards? Bernoulli's principle. That's Bernoulli's principle right there, isn't it? Right. So let's take a look at Bernoulli. Right. So here's what I'm saying. Here's my fish and this pipe system. Actually, I got a few changes going on. I got a difference in pipe size, which is going to change the speed, and that will change the pressure by itself. But hey, I've also got an elevation change. Like that could change the pressure too, couldn't it? Right? I think both of those factors, the fact that you're going to a small pipe to speed up the water, like that should decrease the pressure. Also, the fact that you're changing elevation, you're going up, that should also decrease the pressure too, right? Right. So both those factors together. Right. Right, now where's this full equation coming from right here? Right. This is actually yeah.
So if you had a tank of water and a fish in it on the surface of the earth, and you had a tank of water with a fish in it in a vacuum, would they feel the same pressure, or would you feel different?
Ooh, that's a good question too. Yeah, if you have so let's go back to okay, yeah. Tank of water, right? If the fish is in a tank of water, and let's say there's no air pressure above versus if he's in an atmosphere, because does the whole atmosphere push down with one atmosphere pressure? Yeah, and you would experience that too. Actually, I can kind of show that with maybe dig up that YouTube. Here it is. Right, this YouTube right here. You guys see in the equation, I actually did put pressure of the atmosphere, pressure above. Yeah. So if you went to a different planet, suppose it was like had double the pressure that it does on Earth. You had like 2 atmospheres of pressure pushing down. Would you feel that if you're swimming down in here? Yeah, you definitely would. It would feel more pressurized. Okay, if it was the same amount of water. Okay. Right. Yeah. See how that. All right. So let's do say where does this come from? Now this looks like a lot. I see. Guys, how many terms do you guys see here? How many terms? 6. I see 6 terms, right? 6 terms, 3 here and 3 here. I'm going from point 1 to point 2. How many guys think that kind of looks like sort of conservation of energy type thought process? Does it? Because I got point 1 here, I got point 2 here, and I'm adding up a bunch of terms. Okay. This is actually conservation of energy in disguise. It's conservation of energy, but not in terms of energy. It's in terms of pressure. And I'm going to show you guys that that's true. So let's do a conservation of energy here. Could you guys say that some energy in general? Oh, if you write landscape, that might be helpful for this one because it's going to be a long equation here. Just some general energy plus, guys, what's the formula for gravitational potential energy? MGH. Okay, and I'll do it for initial condition. And how about if something's in motion, it has what kind of energy? Kinetic, 1/2 mv squared. Okay, and I'll say initial. So these are all initial conditions. Then I'll say somewhere later in the system. So I'll say equals, that will show conservation. So somewhere else it has to have the same amount of energy in joules. Maybe have some different kind of energy. Maybe it's thermal energy or spring energy or whatever kind of energy it could take, right? Plus maybe it's change elevation. So I got some different MGH. Plus maybe it's change speed. So I have some different 1/2 mv squared. So little subscripts to show initial and final. Okay, is that okay? Right. Now, oh, how can I here? Maybe I'll kind of work towards the end result. How can I make this start to look more like this? All right, I got all my terms sort of in place. Right. Like let's look at the MGH turns into rho GH. Right. How do you go from mass to density? You have to divide by what?
Volume.
Volume. Hey, can I take every one of these 6 terms and divide by volume, 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 volume? Yeah. As long as I do that to all 6 terms, it's algebraically consistent. Okay. And this right here, you guys just told me is equal to what?
Density.
Density, mass per unit volume, which is also right here. There's density. Also right here, mass per unit volume is density. Mass per unit volume is density. Those are all density, right? You guys know this is capital V for volume, right? As opposed to this lowercase v is v. Okay. And I bet some of you guys are catching on here. What do you guys think? Energy over volume, if you divide that out, what term do you think that would work out to be? Pressure. It sure is. So I have some initial pressure, as in like the internal pressure in the system, like this fish swimming around, feel some pressure on him, right? Plus, I got rho GH, and this rho is the density of what?
Water.
Yeah, the water. The fluid water, right? Plus 1/2 rho V squared equals, and then some internal pressure plus rho GH final plus 1/2 rho V final squared, right? So by changing the speed of the fluid, which you can do by just changing the pipe size, what you guys just saw about conservation of flow, that will change the internal pressure. Also by changing the height, right? If you have a height change, that could change the internal pressure too. So let's throw some numbers on here. Let's say this initial pressure is like, let's say it comes out to like 100 units. I don't know, 100 pascals or whatever. Okay. Plus, let's say this rho GH initial is like 10 pascals. Let's say this 1/2 rho V squared is like another 10 pascal. I'm trying to give you guys a real big picture. Just say you ran all the numbers and comes out to those number of pascals, right? And let's say we're working on this picture right here. You guys see this picture? Right. So if this fish goes up elevation into a smaller pipe, and I want to know what new pressure does this fish feel right here? Right. Now, guys, if it feels 100 pascals here, then here is it more than or less than 100 pascals?
Less than that.
It's got to be less. I mean, for at least 2 reasons, right? Changing speed and changing height, right? So let's say we're solving for what is that new pressure? You guys get that premise? Right. Plus, right. Now, did the density of the water change or stay the same? Stay the same. Is the gravity field also basically the same? Yeah. Right. But we have a taller height. Suppose he was down here like the 5 meter tall level. Now he's up here at like 10 meters up, right? So does this rho GH have to be bigger than or less than 10 pascals? Bigger than, let's call it, I don't know, 20 pascals. Right. So like some of the energy was diverted in, or some of the pressure was sort of diverted into like pushing it up. Right. Right. Also, the fact that he's going into a smaller pipe means what happened to the speed? Increased. So does this term here have to be more than or less than this 10 pascals? More than. Well, let's say it's also 20. I don't know, just to make up a number. Okay. Right. Could you guys solve for what's the internal pressure? What's this equal to now? Huh? 80 pascals. You guys see it has to be 80 pascals to balance the equation? You guys see that would balance the equation, right? Right. 120 on this side balances with 120 on the side. You guys see it? Right. Yeah, that is a pressure decrease, isn't it? Aha. Right. You guys good? Yeah. Yeah.
You could also say that mathematically that pressure has to go lower because the NGH and the 1/2 mv squared go get higher.
Right. Yeah. If these are more and more and more, right? This has to be less and less. Yeah. True. All right. Right, so you guys good there? Guys good? Right. Oh, I do have one more post. I don't think you guys are gonna get AP questions about this, but just so you see it before you graduate high school. Ideal gas law. So this will relate, say you have a balloon roped off. Pressure, volume, and temperature of the balloon. N is how much gas is inside, say in moles. R is just a constant type together, which depends on, well, like, are you measuring volume in liters or cubic meters, for example, or something like that? different values are, right? Just constant, right? But one big thing I want you guys to get out of this class is what are proportional relationships. So guys, let's say I heat up the balloon. When I heat up the balloon, does it contract or expand? Expands. If I double the temperature, let's say the pressure is constant, I double the temperature, the volume would increase by a factor of 2, right? Here's a little curveball question. See if you guys get this. If I go from 10 degrees Celsius to 20 degrees Celsius, is that doubling the temperature?
Yeah.
No. Because I have to use Kelvin, right? I have to do an absolute scale because Celsius could go negative, but you don't really have a negative anything. Yeah, so you have to use Kelvin for temperature. Okay. Right. How about this? What if I leave the temperature the same, but I squeeze down the side of the balloon? What's happening to the volume? It's decreasing, getting smaller. What's happening to the pressure at the same time? Increasing. You guys see an inverse relationship between those two? All right. So there you go. There's a ideal gas law. Right? Everybody good so far? All right. Again, I don't think we're gonna see those questions anymore in this class, but all right. All right. So you guys got your puzzles out, right? You guys got your chapter 9 fluid puzzles. Okay. So here's how we do this. Oh, if you flip it over, the warm up on the back. Just focus on the fluid side. So number 6 through 11 are fluids questions, and they should check all the boxes of all the basic kinds of questions that can be thrown at you. Right. So Archimedes, Bernoulli, Pascal, conservation flow, they're all in there somewhere. Right. I want everybody to try to actually do number 38. Okay. So that's a good question there. And 3 more puzzles. Now, oh yeah, I see some of you guys pulling up your laptops, which is great because you guys can pull up the solutions and make sure, check your answers, make sure, of course, try it yourself first. Right? And I definitely want you guys to check the solutions. Here's why. Most of the solutions I wrote up years ago, some of them I actually have to fix to make them prettier notes, but whatever. Right? This is a new section by AP's book. So I haven't taught fluids to AP. Well, I'll tell you guys right now. Right. So all these solutions I just wrote up a few weeks ago over the break, and I'm not 100% sure that they're all correct. I want you guys to check my solutions and make sure that I'm actually getting them all right. Can you guys do that? You guys see that? Right. So I want you guys to each do 3 additional puzzles because I got to get all these checked. I got to make sure that is number 31 correct? Is number 46 correct? I got to make sure. So here's how I do this. I've got, look at these. Oh, here's number 37. Here's number 40. I'm going to come around with this bucket here. And everybody choose 3 papers out of here. And that's the extra 3 you guys have to do. Okay? Great. And then I'm going to pick this up on Monday. These are going to be due, okay, also on Monday. Okay? Yep.
So we have to do 6 through 11, 38, and then just the red ones?
Yep. So everybody's doing number 6 through 11 on the back. Everybody's doing number 38. And then whatever 3 papers you pull out of here. Okay. These are due on Monday. I'm giving you guys the rest of today and also tomorrow. So the rest of today and all day tomorrow, you guys get to work on these in class. Okay.
Okay.
All right. So with that, let me close down this video. I'm gonna come around and have you guys choose some papers out of this bucket.